Let's talk temperature. And it's unfortunate we don't get too much time to talk about energy in this class. Matter and energy is what this chapter is about. We'll dabble a little bit on the energy of it, but not nearly as much as maybe we would like. But we can talk about temperature. And one interesting thing is the difference between temperature and heat. Those seem like they're sort of similar ideas, right? Temperature and heat. And they're definitely related, but they're not at all the same thing. So let's start just very specifically with temperature, and then I'll give you an idea of how to think of heat. But temperature, turns out, is a measure of atomic or molecular motion. All of the atoms and molecules in the substances that we're looking at, they're moving, okay? And how fast they're moving, essentially, is directly reflected on their temperature. And it goes the direction you would expect. So as, say we have water on the stove or something, we turn up the stove, raise the temperature. What happens to those molecules as the temperature gets higher? How do they move? Yeah, they start moving faster. Okay? So the higher the temperature, the higher that atomic or molecular motion. The more motion, the faster they're moving. Okay? We use a thermometer, of course, to... I'm having trouble writing here. And a thermometer is a way of indirectly measuring that molecular motion, but that sort of the average of the molecular motion of a sample, that is directly related to its temperature. Okay? Heat is a transfer of energy. Temperature is a property of the substance itself. So this container of water or whatever has a specific temperature. Okay? Heat is not a property of a substance. Heat is a transfer of energy from one substance to another substance. Okay? And the temperature is what determines, right, the temperatures of these two objects is what determines what direction heat flows. Okay? What do you suppose it goes to? From low temperature to high temperature, or high temperature to low temperature? What direction do you suppose heat flows? Think about that for a second. If you've got a hot object and a cold object, is heat going to go from the cold to the hot, or the hot to the cold? What do you think? Yeah, heat travels in the direction from high temperature to low temperature. And if that were opposite, then if you had a hot object and a cold object next to each other, if that were opposite, the cold object would be getting colder, right? And the hot object would just continue getting hotter. Of course, we know that if you have these two objects, eventually they'll get into equilibrium where they're at the same temperature, right? Assuming there's nothing else from the outside affecting them. So heat is that movement of energy from something warm to something cold. So when you put your water on the stove to boil water or whatever, the flame underneath, or the hot surface underneath, that's high temperature. So the energy gets transferred from the stove into the water in order to raise the water's temperature. Okay? If you put an ice cube in your water, heat moves from the water into the ice cube, right? Because your ice cube melts. Cold is not really a thing. Right? Cold doesn't transfer. Cold is just kind of the cold is just a lower temperature. Okay? So heat is the molecular energy that actually goes from one thing to another and makes the molecules move faster. Okay? So good way of thinking of that, I think. Don't get temperature and heat confused with one another. We can't really talk about the heat of just a sample. Okay? We can talk about heat as a transfer of energy from one thing to another thing. Okay? That's what heat is. But back to temperature, there are three temperature units that we need to worry about. There are actually more, okay? But the only ones we really need to worry about are Kelvin, the degree Celsius, and the degree Fahrenheit. The little degree sign is part of the unit itself in both Celsius and Fahrenheit. So saying something is 12 degrees, that doesn't really mean anything. That's not a complete unit. So 12 would be the number, and then either degree Celsius or degree Fahrenheit would be a proper unit for those. Okay? So let's start with Kelvin. Kelvin, I'll tell you where these things are mainly used. Kelvin is used in physics, some chemistry calculations as well. Kelvin is sometimes called absolute temperature, and it is the SI unit of temperature, meaning it's a metric and it's sort of the default metric unit. Okay? So let's talk about 0 Kelvin. 0 Kelvin has I spoiled it for you, has a name that some of you are familiar with. What is 0 Kelvin called? That is absolute 0. Okay? 0 Kelvin is absolute 0. Okay? Absolute 0 is more of a limit than an actual temperature, because we can get closer and closer and closer to absolute 0, but we can never actually reach it. So think of atomic and molecular motion. As we're getting colder, the molecules are moving slower and slower. Okay? And if absolute 0 is this limit that we can never reach, what would absolute 0 technically mean the molecules are doing? Yeah, they would stop moving. They're standing still. And there's always going to be some source of energy from somewhere that can get them moving a little bit. Okay? It's impossible to fully isolate them so that they would stop moving. So that's why we can never really reach absolute 0. And scientists go to amazing lengths to get down to fractions of 1 Kelvin unit, but it's even more difficult to get from 1 to 1/2 a Kelvin than it is 1/2 to 1/4, and 1/4 to 1/8, and so on. Okay? You can advance those fractions, but it takes more and more and more effort to go. And they do all kinds of really wacky things. They use radio waves and lasers and stuff to physically make atoms and molecules stand still like that. But even so, it's impossible. Laws of energy and thermodynamics to actually reach absolute 0. So we consider that a limit. If you ever get an answer that is negative Kelvin, you know something went terribly wrong, because we can't even get 0 Kelvin. Okay? So if we look at a couple of these other scales, Celsius is what we use in chemistry, experimental chemistry, most often. In our lab, we will exclusively be measuring temperatures in Celsius. Okay? That's the most common unit for chemistry. You'll see why in a second. Fahrenheit is just the unit of our daily lives in the U.S., and again, the U.S. is nearly alone in the world in making use of the degree Fahrenheit. Most of the rest of the world is come to their senses and use the metric system, but we still love our Fahrenheit. So absolute 0 in Celsius is minus 273.15, which means there are no lower temperatures than minus 273.15. Right? Look at that in Fahrenheit, minus 459.67. So gets way down there in Fahrenheit especially. Okay? The next row in this little table here, let's look at the Celsius value here. What happens at 0 Celsius, 0 degrees C? Freezes? What freezes? Yeah, not everything freezes at 0 C, but water freezes. So we have to be specific about that. Okay, water freezes at 0 C. What happens at 100 C? Water boils. Okay, so the Celsius scale was invented so that it was centered around water's freezing point and boiling point. Okay? The two physical properties of water, the most important chemical substance. So that's why in chemistry we love the degree Celsius so much, because it's totally centered around our most important substance. Okay? Let's compare Kelvin with Celsius, though. Let's look at the difference between absolute 0 okay, and where water freezes. Okay? That's an increase of plus 273.15 Kelvin. Okay? But on the Celsius scale, that's the same distance, right? Degree Celsius. See that? And look at the difference between water freezing and water boiling. Whoops. Get out of here. There we go. That is a difference of 100. And look at the Kelvin scale here, 273.15 to 373. That is a difference of 100 Kelvin. So if you look at the distance or the difference between two temperatures on either the Kelvin or the degree Celsius scale, those differences are the same. That means that let's just draw a little bracket here. That means that Kelvin and degree Celsius have the same size unit. Okay. That means the unit itself, okay, is the same size. The only difference is where 0 is set. In Kelvin, 0 is set at absolute 0. In Celsius, it's set at 0 C. I mentioned that Kelvin is used for some calculations, probably not as much for us in this class, but there are certain types of calculations where if you're using a value, 0 in that value has to mean 0 of the actual property. So that's what the Kelvin scale is. It's absolute temperature, meaning 0 Kelvin is 0 temperature. And every temperature above that is some measurable temperature. 0 on Celsius is just another temperature like any other temperature. Okay? And if you're talking about temperature differences, that's totally fine. But say you have some kind of equation and you're dividing by temperature. Kelvin, that totally works just fine because you've got all just regular numbers for Kelvin. But what if you're dividing by temperature and your temperature happens to be 0 C? Dividing by 0 makes really bad, weird things happen mathematically. And then negative on Celsius, that's not negative temperature. That's just on the other side of this value that we've decided to be 0. Okay. I've also heard some weather broadcasters get this a little bit wrong, like saying it went from 30, even like in Fahrenheit, that it went from 30 Fahrenheit to 60 Fahrenheit one day to the next, saying that that doubles the temperature. Well, that's not a double of the temperature. You would have to use the absolute scale, going from 100 Kelvin to 200 Kelvin or something. That would be an actual double of the temperature. So be a little bit careful about that. It's one of those things that bothers me, I guess. Is this our first appearance of Chemistry Cat? Might be. You guys get it? Hear about the guy that got frozen to absolute 0? He's okay now. So yes, Chemistry Cat will make various appearances. He will take over the duty of offering all the various corny chemistry puns, so I don't have to. These equations right here convert between Kelvin and Celsius because the unit is the same size. All we have to do is either add or subtract 273.15. It's like one scale just got slid over. Okay? So that's just a matter of adding or subtracting. And then it's just a matter of picking the correct equation, right? When you have a value like this equals, and then stuff you have to do over here, then this one is your answer. So if we want an answer in Kelvin, we have to take a Celsius plus 273. Or if we want an answer in Celsius, we have to take a Kelvin minus 273. That would just be like solving this one for that value. So if I have 38.0 degrees C, that's about body temperature, okay, in Celsius or something like that. And I want that same temperature in Kelvin. Should I add or subtract? Yep, we'll take that first equation right there, 38.0 plus 273.15. 311.15 is what your calculator would tell you. But We have to be concerned with where the uncertain digit is in that. Okay? We never are able to escape having a properly rounded answer with the proper number of digits to it. So when we add or subtract, what is the rule? What kind of numbers do we have to look at when we're adding or subtracting? We have to look at decimal places, and our answer will be limited by whichever of those values had the least, had the fewer number of decimal places. Okay? So what should this answer really actually be rounded to? Yep. So let's count decimal places. All right, here's our uncertain digit. 1 decimal place. 273.15 is not exact. It has to do with a very precise measurement of water's freezing point, but we've given it to you with 5 sig figs or 2 decimal places. Okay. So our uncertain digit is going to land right there. 311.2. And if you're still thinking that that's made that answer worse, then remember 38.0 is not exactly 38.0. 38.0 could be 38.1, could be 37.9. Okay? That means we have variation happening in this first decimal place here, which makes the second decimal place totally irrelevant. If this one is varying, then it's just random all after that. So all we can have is one digit that's varying with repeated measurements. So make a little note to yourself that for these Kelvin Celsius, okay, use decimal places to round a degree Celsius Kelvin calculation, okay, in either direction. So don't forget about that. Mastering chemistry, I believe, on these is now programmed to do this correctly. It took me a couple of years of bothering them to make sure that this was actually done correctly. If you round, a lot of times if you round it wrong, it'll still actually give you credit or most of the credit, but it'll complain to you about it. On a quiz or exam, in order to get full credit, you need to have a properly rounded answer. Okay? So that's not too bad. I think we can all add or subtract, right? Anybody have questions about that? Now, when we want to talk about Fahrenheit, let's go back up to our little table here. The Fahrenheit scale is actually not a bad scale for weather reports, right? I mean, 0 and 100 is all based on water, but we don't want to be in any place where water happens to also be boiling. So the Fahrenheit scale, pretty convenient for daily life, right? Because below 0 Fahrenheit, you're not entirely happy with the temperature, and above 100 Fahrenheit, you're also not entirely happy with the temperature. So it works out pretty well, I guess. Really, what that came from is originally 100 Fahrenheit was as precisely as they could measure body temperature, right? 98.6 is what we know it now, but before it got much more precise, 100 Fahrenheit was originally where body temperature was thought to be. And 0 Fahrenheit is how cold you can get saturated salt water, ice water saturated with salt. That gets down to 0 Fahrenheit. So let's look, sort of like we did with these others, at the difference between water freezing and water boiling, right? 32 and 212, that's a difference of 180. So not only is 0 at a different place, but the unit is a different size. Okay? So everybody understand how these bottom 2 rows are the same temperatures on all those scales. Okay? And a difference of 100 C actually ends up being a difference of 180 F. So in that same difference of temperatures, we've got more Fahrenheit units, right? So that means the Fahrenheit units are smaller. We've got 180 of them in the same distance that there are 100 degrees C. Okay? But that means the conversion is sort of two mathematical steps. We have to get the unit the right size, and then we have to get the zero in the right place. So that's why there are two parts to the temperature conversions. The one we usually see is Fahrenheit being 1.8 times degrees C plus 32. And then if we solve this for Celsius, we have to subtract 32 first and then divide by 1.8. So that's where these parentheses are. But it's super, super important that you get those order of operations right. Okay? Let's just make a little note to ourselves what order we actually do these here. If you have a Celsius value and you want that to get into Fahrenheit, should you multiply that first, or should you add the 32 first? 1.8 times degrees Celsius value plus 32. What do you do first? Multiply. That's order of operations. Multiplications happen before additions. So that's important. And you should prove that to yourself by doing it the wrong way. You'll get a totally different answer. What about over here when you see an equation like this? You've got a Fahrenheit and you want to turn it into Celsius. What do you do to that Fahrenheit first? Yeah, we've got this in parentheses, okay, just as a reminder, but you absolutely have to subtract first, not divide first. You will, like I said, get a totally different answer. These equations are on the conversion sheet. The one that's on the inside front cover of your notes packet. They're in the upper right corner there. I give them to you in two ways. I think this is the simplest way, but 1.8 is 9/5. So sometimes you'll see it like that. Divided by 1.8 is the same as 5/9. So should I put that over here? Divided by 1.8. So it's sometimes listed with those fractions, but because it's 9/5 or 5/9, that part of the equation came from the fact that there are 180 Fahrenheit degrees per 100 Celsius degrees. Okay? That's sort of a ratio of 1.8. So that 1.8 is exact, sort of by definition. Okay? The 32 is exact by definition. So we have to be careful, to be a little bit careful how we make use of our digits in something like this. Let's take a warmish summer day, 85 degrees Fahrenheit, and convert that to Celsius. What should I do first with that 85? We're using this equation, right? If we want an answer in Celsius, I better subtract 32. That's 53. You can do that in your head. Then divide by 1.8. Okay? So why don't you get your calculators out? I'm going to have you do this and one other one. If you don't have your calculator with you, make sure to try this afterwards. What's your calculator tell you? Somebody say that a little louder? Yeah, 29 with a lot of fours. Okay. And 4 repeating is not a proper answer. We have to figure out how to round this. Okay. Couple of issues here. We have an original value, 85. That would be 85 plus or minus 1, right? Essentially, an uncertain digit right there. Subtracting the 32, subtracting that exact value doesn't change the place of the uncertain digit, so we're still right there. Okay? And then we divide by this exact 1.8, so we need to look then at how many significant figures that had. Even if you multiply or divide by an exact number, you retain the significant figures of the measurement you started with, right? So what should this answer really be rounded to? Yeah, it should be rounded to two significant figures. Okay, it should be rounded to 29. Okay, so let's make a little note to ourselves for Fahrenheit and Celsius. Use the sig figs of the original temp to round a Celsius Fahrenheit either direction conversion. Okay? And it doesn't matter which of those you use, you're still doing a multiplication of a measurement which will preserve its significant figures, plus exactly 32 won't change anything. Okay? So it's still sig figs from there. Here, subtracting 32 doesn't change. We're dividing by an exact number, but we keep the significant figures of what we had originally. So, what do we have to do if we want to go from Fahrenheit to Kelvin? Yep. So if I want 85 Fahrenheit in Kelvin, we would have to first do 85 Fahrenheit to Celsius, which we did above. Okay. And then Celsius to Kelvin, let's just make a little, right, Fahrenheit, Celsius, Kelvin. Okay. Celsius to Kelvin, what should I add or subtract? It's going to be this one. Okay. But here's my question for you. Should I do 29 plus 273.15? Or should I do 273.15? Add both of those. I want you to see the result of both of these. What do you get when you do the rounded 29 plus 273.15? What's that? Okay, 302.15. And then this unrounded one, what is that? $594444. Okay. With adding, we're limited by decimal places, right? 2 decimal places here, 0 decimal places here. So what would this answer be rounded? Just 302. Okay. Would this one be limited by now the 2 decimal places over here? Nope. Why not? Where is the uncertain digit in this one? Yeah, look what we did. We underlined that 9 as a reminder that that's the uncertain digit. Okay? Uncertain digit's right there. So even though that has 2 decimal places, and even though the unrounded value has as many decimal places as we want, okay, the uncertain digit is still here in the ones place. Okay? And if that's the case, then what would that one be rounded to? 302? Oh, 303. but still 0 decimal places. Okay. Which one is a more correct answer? 303. What little rule did we violate right here? Yeah, you're only allowed to round at the very end. Okay, let's draw some x's here. Okay, don't use a rounded value. There are times when using a rounded intermediate value like that actually changes your final answer, right? And this is one of them. Now, the variation will usually just happen in the uncertain digit, and that's not the worst thing, but even so, to be precise, I will usually have problems where I can tell if you've done your rounding properly. Okay? And if you've done all of your rounding properly, if you've kept plenty of extra digits, okay, past your uncertain digit, then you should get exactly the same answer that we're expecting to get. Okay? So that's the arithmetic on that I don't think is too difficult. Just put a little bit of thought into how these answers are rounded. Okay? Yeah, go ahead. So when we rounded like this one right here to get that one, we only look at one digit. We only look. Oh, how many do you use? It would be best if the whole thing just stayed in your calculator, right? If you got the answer, your whole calculator would be filled with 4s, and then you could just leave that in there and do plus 273.15. That's the best. If you have to write down an intermediate value and type it back in, you should use at least 2 or 3 extra digits past. Yep, that's a good question. I think the textbook maybe uses 2 extra digits or something, or two or 3, but okay. But whenever possible, it's always best to keep the whole thing in your calculator. Okay. Other questions?